Now, 28 question we set last year, right? Now, this part came from the other lecturer. We have statistical analysis. So we are asked to solve for standard deviation, variance, and percentage relative error, right? Now, I know I've actually not done errors. So I'm going to use up for this to also explain what errors are mathematically. So you're asked to solve for this. Now, first and foremost, for you to solve for standard deviation, you must first of all solve for mean. You must solve for mean. The question says the concentration of iron in ppm in 6 replicate soil samples are 19.4, 19.5, 20.3, 19.6, and 20.1. If the technique concentration is actually 20.0 ppm, determine the standard deviation, the variance, and the percentage relative error. Now, here, let's start with standard deviation class. Now, what is the formula to solve for standard deviation? Standard deviation has this symbol of S. We have two types. We have the sample and we have the population. So we have thank you very much. If we have 6 replicate value, we have 19.4. Please, I posted information on the WhatsApp. Just check. Right? 19.4, 19.5, 20.3 is question number 27. Now, please, standard deviation has the formula. We have summation of x minus x bar all over n minus 1. Now, here x is equals to the mean. Now, x equals to individual value, and n equals to number of data. In the size of value. Class, you cannot proceed to solve for standard deviation without first of all solving for the mean. You must first of all solve for the mean, right? And how do you solve for this mean? My mean is x bar. Mean is sum of the values divided by the number of data. So we have 19.4 plus 19.5 plus 20.3 plus 19.6 plus 19.8 plus 20.1, all divided by half in class, 6. 19.7. Now look up. This guy, it was one decimal place that we have here, right? So let's just maintain the order. So answer is 19.78, but we need to give you one decimal place to correspond with this guy, right? So let's say when you subtract, when you approximate, this becomes 19.8. So our mean value is 19.8, right? So we've gotten our mean. Now the next thing I'm going to do is that okay. Now let's take off this. Please look up. You want to solve for standard deviation. This is what you're going to do. You must draw a table. The first one is your x table. It's compulsory. You must draw your table. What is the first value here? 19.4. You actually place the individual values as x because I told us that x is individual values. The next x is 19.5. The next one is what? 20.3. The next one is what? The next one is what? The next one is 20.1. That is this. Now the next column you're going to create is mean deviation. Now this particular table is very, very important, class, because it tells us how much the value differs from the mean. So we're going to do it together. How do we get, class, how do we get this table? Please look up. We're going to get this table by taking the value of x and subtracting it from the mean for each of the values. You understand? For this one, x is 19.4, the mean is 19.8, right? So we say 19.4 minus 19.8, that is minus 0.4, right? Now, the mean is 19.8, our individual x is 19.4. So when you subtract this from the mean, you have this. The next one is 19.5 minus 19.8, this minus what? 0.3, right? Now, how about in order to save time in exams? Okay, let's just complete this guy. 20.3 minus 19.8. That's what? 0.5. Now this is minus 0.2. This minus 0. This alright. Sorry. The next column we are going to create is x minus x squared bar. Please come here, come back to the formula for standard deviation, please. There's always raised to the power of 2 here. Please ensure you put that. This standard summation of x minus x bar always to the power of 2. Okay? Alright. So how are we going to get this? Please look up. What we are simply going to do, we are going to square this value. Right? Yes. Ignore the minus because minus times minus is always plus. Yeah. So square this 0.4 squared. Give us what? 0.1. This is 0.16. This one is what? 0.09. This is 0. What? 0.25, 0.04, 0.00, 0.09. On this side, the next thing you're going to do is that remember, from this standard deviation, this side stands for sum. This is summation. Yeah. So you say summation of x minus x bar square. How do we get this? Is for us to simply do what? Out of everything here. So this becomes 0.16 plus 0.0. Now this becomes 0.67. Now say my standard deviation x is equal to summation of x minus x bar square all over x minus 1. Now my x becomes equals to, anywhere I see summation of x minus x bar square, I'll put 0.63. Right? Yeah. Because this is actually what we got from here. So this is 0.63 all divided by n is the number of data instead of value. How many data do you have here? 6. 1, 2, 3, 4, 5, 6. So this is 6 minus 1. So my standard deviation is summation of, we have 0.63 divided by what? 5. So you say 0.63 divided by the 5, and then take the square root of that. So this standard deviation becomes 0.355. That is the standard deviation for that. Now, I wanted to show us a shortcut earlier, but I just said let me complete this. In exams, the time frame is always very short. In order for us to beat the time, listen, what do we normally do? Instead of me to do this guy, right? I'm going to just, this is what I mean. Let me show something. In exams, to avoid wasting of time, because time matters a lot, right? Instead of me to do this table, and see what I do this table, why don't just square this guy directly? You understand what I mean? Now let me show something. I'll come here. I'll say this guy directly is square, right? Now this is what I will just look up. Remember, our mean was equal to 19.8. Is not so. So I'll come here. What is x? X for this guy is 19.4, right? So I'll say 19.4 minus 19.8. That's minus 0.04, right? Square it at once. Do what? Square it at once. In the first case, you have to first of all write it down. and then d the square. You understand? But instead of me to do this and do this, I just simply say this is supposed to give us minus 0.04. 0.4, right? Instead of writing 0.0, you square this guy at once. This will now give us what? 0.16. 19.5 minus this is supposed to give us minus 0.3. Also, instead of it to write 0.3, just square it at once, right? This becomes 0.09. Just what I got it here. 20.3 minus 19.8 is 0.5, right? Instead of it to write 0.5, you square this becomes 0.25. This is supposed to be minus 0.2. You square this guy, this becomes 0.04. This is supposed to be 0.0. When you square it, you see the same thing. 20.1 minus 19.8 is 0.3. When you square this guy, it becomes 0.1. Now, if you do summation of x minus x bar squared, you see going to give us 0.1. 63. So you come back here and you set your 0.63 here, and then you get your answer. All right. Variance equals to standard deviation called square. That's square of standard deviation. That's the formula for variance. So whatever the standard deviation is, just square it. So my variance will be equal to our standard deviation again is 0.355. When you square this to 6, finish.
Teaser, I have a question.
Is that?
In this place, I know when to square this one to get the answer. Yes.
This one, when it's squared, it's already squared. These values are the square. 19.4 minus 19.8 is 0.6. When you square this, they have differences.
Okay.
We already squared it. This
Then,
was
then that's by the summation.
no, you solve this thing. You don't like this thing is solved.
Yes.
Like this thing now, to solve all these things now, we leave all this. This symbol means solve. This solve we have is what we have here. So you're solving everything you have here. So this formula now has summation of x minus x bar squared. So this numerator is just going to put 0.167.
Understand?
Alright, so that's for that for variance. Okay. So before I actually proceed to solve the next question, let me quickly solve for other parameters. Now, what was the other parameters? The one I listed out first for us. Not the one in the exam question. Okay, let's say, what if you are asked to solve for relative standard deviation? Now, the relative standard deviation is equals to standard deviation all over the what? Mean. That's the value. Now, what is our standard deviation? 0.355. The value for the mean was 19.8. So this is 19.8. What's the answer to that?
0.0179.
0.1.
0179.
0.0179.
79.
All right. Now, please look up. Just in case in exams, what if in exams you're asked to do percentage relative standard deviation? Or they say percentage standard deviation. Please listen up. What if you were being asked in exams to give the standard deviation in percentage or in parts per million? Do you understand? So what is a percentage standard deviation? For me to get that, is for me to simply multiply the value of standard deviation by 100, which is percentage, which is parts per million multiplied by 1 million. I repeat, what if you were asked to solve for standard deviation in percentage, right? Whatever your answer is, times what? 100. In part per million, times what? 1 million. Part per thousand is half times what? 1,000. Same thing here. Relative standard deviation is standard deviation all over the mean. If you were asked to solve for the percentage relative standard deviation, it's simply going to be standard deviation all over mean times 100, that's for percentage. If you're asked in percentage, always multiply by 100. If you're asked in parts per thousand, multiply by what? 1,000. Parts per million, multiply by what? 1 million. So that is it. So if we are done with this guy, let's look at error, right? Then I'll come back to the question they gave us here. Let's look at error. All right, so we want to look at acid-base indicators. Indicators are weak organic acid or base whose undissociated form differs in color from its conjugate base or acid. Now let's look at the behavior or dissociation of indicator subheading. The behavior is also known as dissociation. Please note that these guys, they are weak organic acid or base. They are very, very weak. They need to be weak so that they don't interfere in the reaction. Because you must always add this in a reaction you're carrying out. If the concentration is not as weak as it's supposed to be, to interfere with the reaction, of course, affect your result. Now, class, we have two types of indicator. We have the acid type. We have the acid type indicator, which has a symbol of H, I, N, D. This H is very, very important to show that it is an acid. Acid will always give out H. That is why this H is present here. Now, the next one we have a base type indicator. Now, this guy does not have H. This guy is going to accept H, while this guy is going to give out H. So in case you see HING, this stands for acid type indicator. Why do we call it acid type? Because it's always going to give out hydrogen alone. This guy is base type because it's going to accept. Now, we want to look at the behavior of this guy. Behavior is centered on dissociation. Class, remember that weak acid is always going to dissociate partially. Is it also? Which is going to give us H plus what? A minus. So if an acid type indicator dissociates, we're going to get something similar to this, which is, so we say for acid type, dissociation slash behavior. Now, acid type indicator is HIND. Now, two things in hope. You just write this equation. You can decide to add water or not. If you're writing that of acid, water is optional. But if you're writing that of base, water is compulsory. Water is what? So this is going to give rise to H plus, or let me just add water since there's water here, plus H2O. Please make sure the sign is reversible. Reversible means that this guy is weak, right? Yeah. So this is what is going to happen. This guy is acting as an acid. The water is acting as what? So this guy is going to donate hydrogen. This guy will do what? Accept. So this becomes H3O plus I and what? Minus. This is the behavior of acid type indicator. In exams, if you're asked the behavior of acid type indicator, this is it. How does it behave? It behaves in the sense of donating what? Hydrogen. So that is the behavior. All right. So the next thing we're going to look out for is class. We're going to look at equilibrium constants. equilibrium constant for acid type class. Just like weak acid. If weak acid should dissociate, you can get your K acid dissociation constant, right? So since this indicator is considered an acid type, if it dissociates, there is also a possibility of also having equilibrium constant of this. So equilibrium constant of this guy will be K, you can decide to put this, right? This is because it's an indicator. Or you can choose, you can put what? K, because it is an acid type, right? Now this is going to be equals to equilibrium constant is obtained by taking the ratio of the product concentration to that of the what? Reactant. The product of this reaction is H3O plus and IND mod minus. Bear in mind that this is aqueous, this is what? Aqueous. This guy is what? Liquid, and this is aqueous. Class, water is not going to take part in this equilibrium constant expression. Because in equilibrium constant expression, water is a liquid. Liquid and solid do not take part, right? Aqueous and gas only do take part. So here, the product of this guy, you write the product on top divided by the reactants below. So this guy, the first product is H3O plus. The second product is IND minus. Now all over this guy, we have HIN. Please make sure you don't miss this concentration. This is the acid type indicator, equilibrium constant. Alright, so please write this so that we can look at the base. Alright, for base type indicator, let's try the behavior. The behavior or dissociation. Base type indicator is this. Alright, so we'll start here by saying this is the base type plus water. Now, reversible. This guy is a base, right? So this water is acting as an acid. In the previous case, the water was acting as a base, and that as an indicator was donating. So here, this indicator is a base, when the water is acting as a water. So this guy will donate hydrogen. This guy will accept. And once it accepts, this guy becomes what? This guy. Let's remove this guy. Let's remove this G. Let's remove the G. Let's just use this as base type. So when this guy receives proton, it becomes what? The reason why we are putting plus is because this guy is neutral. Right? If something is neutral and plus, if plus comes here, it's going to be positive. And if it was minus, that is going to be neutral. See, just like somebody saying 0 plus 1, that is going to be what? Plus 1. But if someone should say minus 1 plus 1, that's going to be what? 0. So this guy is neutral, so it's seen as what? 0. Proton is having plus 1. So 0 plus 1 is what? Plus 1. So that is why we have this. Plus OH plus minus. We have aqueous. This is a behavior of base type indicator or the dissociation. This is how it behaves inside water. Now, equilibrium constant expression is going to be KB. So once again, the product is this. So the concentration of the product times that of the other product divided by this. Once again, we're not going to add behaviors. So this is a behavior, and this is a non-constant expression. Okay. All right. So let's look at the suitable indicator for different type of titration. Suitable indicators for different titration. Now the first one we have strong acid titration versus strong base. But the suitable indicator for this guy is phenolphthalein. Phenolphthalein, even though most of the times you can use methyl orange. Methyl orange cannot be used here, but between methyl orange and phenolphthalein, which of them is the best? It's phenolphthalein. But that does not mean we can also use methyl orange. We can use methyl orange, only that we're going to use more volume of solution. That's we're going to use more volume of the acid from the direct. But if you use phenolphthalein, you use less volume of the acid. Many of us may not really understand what I'm trying to say. But I'm saying that if you use phenolphthalein, the end point is going to come faster. When you use methyl orange, the end point will come much later. Right? Because we need to combine this guy. This guy changes color at pH. Phenolphthalein changes color at pH greater than what? 7. While methyl orange changes color at pH 3 to 4, around that area. So if you're using acid, you need to pour in acid to convert the base from base to neutral, right? And when you add more acid, you take it to acidic. It's not necessary. Just so that the suitable indicator for strong acid and base, the best one is phenolphthalein, right? But you can also use what? Methyl orange. Now the next one we have strong acid versus weak base. Nice one. The suitable indicator here is methyl orange. Methyl orange. For strong acid versus weak base, suitable indicator is methyl orange. The third one is strong base versus weak acid. Please, the suitable indicator here is phenolphthalein. Take note of that. Strong acid versus weak base, methyl orange is the suitable indicator. Strong base versus weak acid, phenolphthalein is the suitable indicator. Now, what if we have weak base versus weak acid? Please, the answer, there is no suitable indicator. Like two dummies coming together. No suitable indicators. Alright? Strong acid is a strong base. The most suitable indicator is phenolphthalein, even though methyl orange cannot be used. I told us that if you use that, the rating, I told us. Strong acid versus weak base, methyl orange is a suitable. Strong base versus weak acid, phenolphthalein. Weak acid versus weak base, or vice versa. No suitable indicator. So please make sure you hit the subscribe button. Thank you.